Given two sorted linked lists, we have to merge them into one sorted linked list and return the head node. We'll do this by using a pointer to traverse through the two lists and merge them together. To start, we are given the head nodes of two linked lists, list 1 and list 2, which are shown in the diagram. We'll also be using this definition of a linked list here. The first thing we'll do is create a new node to start building our answer, and we'll call it head. Then we'll create a pointer called current, which I'll represent with this big red block here, and we'll point it to head. Then we'll enter a loop that says while list 1 and list 2. In other words, while list 1 and list 2 both are not none. Both of them point to a node right now, so we'll enter the loop. Now we check to see which list node has the smaller value, and we'll link that to the current node. Right now, the value of list 1 is 1, and the value of list 2 is 2, so we'll enter this if block and set current.next to point at list 1. In other words, what we're really doing is moving this arrow to point at the same node that list 1 is pointing to. Then we'll advance the list 1 pointer by setting list 1 equal to list1.next. Then, at the end of each loop, we'll also advance the current pointer by setting current equal to current.next. Then we'll do it again. Now list1.val is 3, and list2.val is 2, so the value of list 2 is smaller, so we'll jump to the else block. We now do the same thing, but this time with list 2. So first we'll point current.next to list 2, then we'll advance list 2, then advance current. Next, list 1 and list 2 both have the same value of 3, so it actually doesn't matter which node we link next. But the way we wrote it here, 3 is not less than 3, so we go to the else block again, and just do the same thing and attach list 2 to current. So you can see that by using this method, instead of creating an entirely new linked list with copies of the sorted nodes, by manipulating the pointers instead, we can modify the lists in place and save time and memory. We're near the end here, so let's look at the last iteration. List1.val is 5, and list2.val is 4, so we'll point current.next to list 2 and move up list 2 and current. But now notice that list 2 has reached the end and now points to none. So when we check the loop condition, list 2 is none, which makes this condition false. At this point, there's no need to iterate through the rest of the first list because we know that the rest of the list is still in sorted order. So to finish up, we can just point current.next to the list that's not none, and we're done. So that's what this line here does, and let me take some time to explain exactly how this line works. List 1 or list 2 will return whichever one is not none. So if list 1 was not none, then list 1 would be returned, and we'd set current.next equal to list 1. But if list 1 was none, then this would instead return list 2, and we'd set current.next equal to list 2. If both of them were not none, then it would just return the first argument that is evaluated, which is list 1. But at this point, we know that only one of the lists is not none. So what we're really saying here is, point current.next to the list that still has nodes left. If this is confusing to you, you can also write it like this. If list 1 doesn't equal none, current.next equals list 1. Else, current.next equals list 2. It's the same thing, and this is a totally valid way of writing it, but I just wanted to show you the shortcut since it seems popular. So here, list 1 is the list that still has nodes left over, so we'll point current.next to list 1, and this automatically links up the rest of the nodes. Now our new linked list goes from 1 to 2 to 3 to 3 again, then to 4, and then 5, 6, and 8, and remains in sorted order. All that's left to do is return head.next, which points to the starting node, and we're done.